Hi, I'm Anika.
And I'm Nikhil.
And for the past 7 to 8 months, we've been working on mitosis detection and tumor grading using deep convolutional neural networks and other machine learning techniques. So it turns out that the amount of mitotic activity in a patient's biopsy slide can tell us a lot about the aggressiveness of their tumor. So we specifically looked at breast cancer, and when scoring patients for breast cancer, what pathologists do is they give them a value of 1, 2, or 3. And they do this by, instead of looking at the entire biopsy slide, they select these smaller regions and count the number of mitoses in those regions. So there are problems with this current scoring method, though. So for example, pathologist scores have a low integrator consistency and can often be inaccurate. Especially in regions where there aren't very many well-trained pathologists, this accuracy greatly suffers. The process is also tedious and time-consuming. And can you really sum up all of that information in that quite large whole slide image into just one of 3 numbers? Not really. So an automated system can fix this problem. And for this reason, mitosis detection has been a really hot topic, with many competitions aiming to detect mitoses in these smaller regions. And it's still a pretty challenging task. As you can see here, there's a similarity between mitoses and normal cells, and mitotic figures are pretty rare inside each region. So the best previous research had an F1 score of 0.78 using convolutional neural networks, which we'll discuss in a couple of slides. So grading the entire whole slide image is an even more daunting challenge due to its immense size and the difficulty in selecting representative regions of interest. So previous methods didn't look at mitotic activity at all to give a patient a score from a whole slide image. Instead, they looked at nuclear features. So in this project, first we aimed to develop a generalizable mitosis detector that outperforms previous results, and then use that detector to build an automated pipeline to score whole slide images. And finally, we explored an application of gene-level modeling.
So first, we built a mitosis detector that acts on these 2000 by 2000 HPF, or high-power field images. We trained a pixel-by-pixel model that attempts to determine for each pixel whether or not it's inside a mitotic region, given a window of context. So as we discussed earlier, previous research used deep convolutional neural networks to model mitotic regions, but we felt they didn't go deep enough. So deep learning is this new paradigm that's changing the face of machine learning. It's this idea that by using large interconnected networks of neurons that signal to each other, it's possible to model high-level abstractions and achieve great success on tasks like image classification and scene recognition. The GoogleNet is one such deep learning model, and we built a GoogleNet with some crucial modifications and trained it to predict for each pixel whether it was inside a mitotic region, given a 139 by 139 window of context. We applied aggressive data augmentation, so random magnifications, rotations, color adjustments, and scaling, in order to increase the network generalizability by ensuring it doesn't come to expect a particular data format. The rarity of mitotic examples was a major problem, because for each mitotic example, there's many, many normal examples. So we needed to develop an efficient learning strategy that makes use of the most difficult non-mitotic examples. So imagine learning vocabulary words from a set of flashcards. For the easy words, you'd probably discard them from your deck as soon as you've learned them. But for the most difficult words, you keep on cycling them through the deck over and over again until you've learned them for good. We use this principle to make a working memory priority queue that stores non-mitotic patches by difficulty. And as you insert new non-mitotic patches into the queue, like in this example over here, then they displace earlier non-mitotic patches, and the queue becomes overall more difficult to classify. We use this queue inside our bootstrapping algorithm. So first, we trained a DCNN on the patches inside a working memory priority queue. Then, in the scouting stage, we search for new non-mitotic patches and insert them into the queue, displacing old examples. In the next stage of the cycle, now the DCNN is forced to learn more subtle discriminative features. It's a self-reinforcing cycle. As the DCNN becomes better at classification, it also becomes better at finding difficult examples. So the DCNN essentially pulls itself up by its own bootstraps. That's what we call bootstrapping. We use our trained DCNN to predict the locations of mitoses. First, we evaluate it pixel by pixel across a high-power field to get a probability heat map. And we apply some image processing to this heat map to accentuate the possible mitoses and pick out the mitotic centroid locations. We compare our list of predicted mitotic centroids to the actual ground truth mitotic centroids and compute precision, recall, and F1 score statistics. We evaluated our method on 3 different competitions, and we had improved results. The only exception was the ICPR competition, in which the low amount of data made it difficult for the bootstrapping algorithm to learn effectively. We also applied our trained 2-pack model to the ICPR dataset, and we had improved results, 0.829 F1 score. And these results indicate that our methods could possibly transcend inter-dataset variation and generalize to new data. So when we saw this, we felt confident we could move on to the next stage of the project.
Yeah, so in order to grade the entire whole slide image, you first need to select representative regions of interest. So while pathologists do this by using their intuition, we use data. So for each whole slide image, we randomly sampled 400 regions of interest and then plotted their nuclei number distribution, as in this chart over here. So the first peak is where there are 0 nuclei, so it's the white space surrounding the tissue. Therefore, we chose our representative regions from the second peak and use that in the next part to get 5 features. So our 5 features are, well, one of them is the mitosis score, the average mitotic probability across all nuclei pixels. And we use this score in the other 4 features and built a classifier to predict what the pathologist score is. And it was able to predict this with a 0.81 AUC, showing our features were predictive. But the thing about this AUC is that it could go either way. So either our mitosis scores are worse than the pathologist scores, or our mitosis scores are better than the pathologist scores. So we investigated this by using each patient's RNA sequence data, and we performed differential expression analysis to find which set of genes correlate with the mitosis score, and then which set of genes correlate with the pathologist score. So we had 2 sets of genes, and then we performed functional pathway analysis and found which functions and pathways were enriched by each of these set of genes. So we found that 7 out of the 8 pathways enriched by the mitosis score genes were related to cell cycle regulation in cancer, while only 1 out of the 4 for the pathologist scores were related to these topics. And in addition, when we analyzed the top 10 pathways related to cell cycle regulation in cancer, we found that they were more enriched by our mitosis score than by the pathologist score. So these good results could be due to our use of continuous scoring, which gives a lot more information than just 1 of 3 numbers, and from the improved results from our mitosis detector. But ultimately, we built a score that's able to understand the underlying genetic mechanisms behind tumor proliferation and mitosis to give doctors more information. So now that we built this effective mitosis score, we wanted to apply it to a gene-level model. So this has the possibility or potential to bypass histopathology image analysis. And how we did this is we used each patient's set of 20K genes and built an elastic net regression model to predict what their mitosis score would be. And when we analyzed the most important features from this elastic net regression model by taking the non-zero coefficients, we found that 6 out of the most important, 16 genes, were already related to mitosis and cell cycle regulation and tumor proliferation from previous research, and we recommend further research to investigate the use of the other 10 vital genes.
To recap, we developed a deep learning-based mitosis detection algorithm that outperforms the best results inside previous competitions. And we did this through harnessing the power of deep learning, as well as developing a novel bootstrap learning strategy that's able to deal with extreme class imbalance. Ultimately, our methods were able to generalize to other datasets without losing performance. We also developed an automated tumor grading pipeline that's predictive of pathologist scores and is even more effective than pathologist scores at identifying the underlying genetic mechanisms behind tumor proliferation. We use these to build a gene-level model and we use this gene-level model to find 10 new genes that we hope future research will investigate. And speaking of future research, these are some of the challenges that we'd like to tackle in the future. The GoogleNet, the improved performance with the 100-layer GoogleNet, comes with the cost of computational intensity. Each whole slide image takes about 15 minutes to completely evaluate. And this can be problematic inside a clinical setting. So we need to develop clever algorithms and parallelization techniques to improve the speed of the GoogleNet, of course, without sacrificing accuracy. We also want to try various ensemble techniques and other methods to improve the performance of the GoogleNet.
Yeah, and due to the computational intensity, we weren't able to examine the entire whole slide image. Instead, we had to randomly sample regions of interest. So we plan to build a more robust ROI selection algorithm that reduces this potential variability by examining more detailed image features and doing bag of words clustering to find the representative ROIs.
Our work can also be extended to use our detailed mitosis features to predict the course of cancer and even possibly recommend tailored treatment regimens. Ultimately, we harness the vast amount of data inside whole slide images to create a score that gives doctors accurate real-time analysis of tumor diagnostics. It's a small change, but it can make a big difference. So we'd like to acknowledge our extremely supportive mentors, Dr. Andrew Beck and Diane Wong.
And we'd also like to thank all of our teachers and our principal inside Monta Vista High School and George Washington University and the Siemens Competition for providing us with this amazing opportunity. Thank you.
Thank you.